leads. Um, Maybe I'll stop there with the introduction and allow him to introduce himself further. John, the floor is yours.
Thank you very much, Bruno. It's a real pleasure to be here this morning. I will just start sharing my screen. Great. Okay, I hope you can see that. Yeah, so my name is John Eiley. I am a researcher at the University of Leeds. This may be somewhere you've not been before. We're a city in northern England. And the reason I'm speaking to you today is part of an initiative that I'm involved in called the Leeds Africa Hub for Data Science and Artificial Intelligence. And what we're trying to do really here with this initiative is connect with researchers, students, anyone who's interested in data science and artificial intelligence across Africa, and make connections with researchers in Leeds on these topics. And I am an astronomer myself, an astrophysicist. I'm going to be talking to you today about how we have some upcoming challenges in astronomy, and how we're really going to be needing the expertise of people who have backgrounds in artificial intelligence, data science, and machine learning. So I'll just give you a quick outline of the talk. So first I'll bring in a bit of a history of astronomy and artificial intelligence as well. Then I'll talk a bit about how we have what's called a bit of a big data problem in astronomy, both currently and in the past and also in the future. Then I'll go through a few applications of artificial intelligence in astronomy. This won't be exhaustive. This will just be a few kind of choice examples that I've thought you might find interesting. And then really I'll talk about the future of AI and astronomy and why we're going to be needing this more than ever, hopefully. And in convincing you that your skills will be very much required in this research field. And then I'll finish by talking a bit about astronomy across Africa and some initiatives that are ongoing at the moment. And then I'll leave you with some resources for applying AI techniques to astronomical data that hopefully you can have a play with and apply your skills to. So I should say, if you've got any questions throughout any of the talk, please just pop them in the chat, or I can catch them at the end. Whatever works best. So, talking about the history of astronomy, well, really, I think it's fair to say that astronomy is really the oldest science that we have. It's founded many aspects of modern life. You think about calendars, think about navigation. All of these have roots in looking at the night sky and understanding where we are, timekeeping, all of this kind of stuff. It provides a reference frame for all of those studies that go back to really to antiquity, before historical records really began across the world. It has foundations in geometry and really even mathematics itself. If we go back to counting and things like this, it really is one of the basic research areas that has been going on since records began, really, and even before then. And I thought this was a really nice example of this kind of thing. So this is the Nabta player structure in Egypt, which is about 7,000 years old. It's been estimated. And this has been called the dawn of observational astronomy. So this is really no different to what we do with astronomy at the moment. It's just a little bit less sophisticated than what we have at the moment. And what this was used for was to track the motion of the sun, to find out things about when the next solstice would be appearing, and track, it's thought to track the seasonal changes and the monsoon season as well. And this is, as I said, this is no different to what we use now. We use facilities on the ground to observe the stars and other objects in the sky and try and understand their place in the universe. So this has been going on for many, many thousands of years. On the flip side to that, I think it's fair to say that artificial intelligence is really one of the newest sciences that we have. And this has really been, I think, enabled by the computing revolution of the 20th century. So the term was first used in about 1956 at a particular conference, but it was imagined much before that. So I'm just showing a few playful examples there of the Tin Man from The Wizard of Oz. This is probably one of the first examples in literature of something that has artificial intelligence. And obviously there's the short stories from Isaac Asimov in I, Robot as well at the beginning of the 20th century. And this has really been a rapidly developing field, as I'm sure you're all aware, with huge recent advances. So what I'm kind of setting up here for the talk is how will artificial intelligence and astronomy interact both now and in the future. And I should say that I'm using the term astronomy throughout the talk, but really there's no difference in my mind between astronomy and astrophysics. They're kind of the same research area, just the terms tend to be used interchangeably. So we'll stick with astronomy for today. So astronomy is often considered to be a research area with big data. So we have lots of data in astronomy, and of course we're looking at the whole universe. So we have a whole universe of data. And what I'm showing here in this graph is the year that a particular telescope or observational facility has seen what we call first light. So that's when it's first observed light from the sky, plotted against its data volume over its lifetime. So you don't need to know exactly what each of these acronyms mean, but I think what I hope you can see from the graph is that the data volume of various facilities is increasing with time. So we go from here from about 1995 up to 2000 up to, we stopped the graph here at 2015. And the important thing to note here is that the y-axis on this graph here is logarithmic. So each of these axis ticks is a factor of 1,000 increase. And actually in 2015, the kind of the trend line, if you will, for this relationship is approaching what the combined uploads to Facebook are per year. So the volume of data that we're dealing with in astronomy is comparable to really large scale commercial enterprises in terms of digital assets and digital data, digital storage. So this is really kind of the realm that we're looking in. That we have a lot of data. We have a lot of data to understand, analyze, and process. So thinking about how we've dealt with those big data problems in the past, we've actually used a term that I think it's fair to say is non-artificial intelligence. So how can we look at all that data and understand it? And what we've used is people. Initially, this was individual researchers or teams of researchers to look at data, but as data volumes grew, we have actually invoked the public to help with this. So this is a term called citizen science. And the definition of this is, there are several, but this is research conducted with participation from the general public or amateur non-professional researchers or participants. And if you want to have a look at some examples of citizen science efforts, there's a link there in the slide that I'll also post elsewhere for you to check out. And basically there are many different projects that ask the public to help to get involved and actually analyze the data themselves. And this, if we ask enough volunteers to do this, then this makes the problem scalable, and we can look at huge data sets with the help of interested parties in the public, or perhaps even researchers in other fields who are just generally interested in the results of these projects. So one of the first citizen science projects really that kicked this off in astronomy was called the Galaxy Zoo. And the aim of this was to classify the shape and structure of many thousands of galaxies observed by the Hubble Space Telescope. So I'm sure you've all heard of the Hubble Telescope. There's the image of that there. It's still operating, launched in the 90s, and it's still operating in orbit around Earth at the moment. It's one of the most productive scientific instruments that has ever been created. And it was really a huge step change in terms of our ability to observe the universe, because we moved the telescope up into space to get away from the distorting elements of the atmosphere, and that allowed it to really create these beautiful, very sharp pictures of the universe. And this actually shows a collection of galaxies that have been observed by Hubble. And you can see the really intricate detail in many of them here. The kind of what we call grand design spiral galaxies, mostly in this picture. And we can see the individual star-forming regions, the central bulges of the galaxy, and the spiral arms that are going around. And we think that the galaxy that we live in, the Milky Way, is similar to some of the galaxies here on the top row of this image here. So, one of the main research questions in this is, what is the variety of galaxies that we observe? How do they change over their time? Obviously, we can't watch them evolve, but we can look at many different examples of galaxies and try to understand if there's an evolutionary sequence and how they might have formed, what they might do, how they might interact, and what that means for our place in the larger universe. So this was really the story behind that research area, but it's, as I mentioned, it's a bit of a big data problem. So the data set that Galaxy Zoo worked with was approximately 900,000 images, nearly 1 million images. And if someone was to look at that themselves and go through and classify each of those observations, working 24 hours a day, 7 days a week, that would take you a total of between about 3 and 5 years, depending on how quickly you did this. So obviously, that's not really something we want an individual person to do. I would feel very sorry for them if that was given to them as a PhD project or something like this. But so obviously we need to think about using a different method to analyze that data. So we can ask the question, what about if we use more than one person? And this is where the Galaxy Zoo or the Citizen Science Project comes in. So the Galaxy Zoo effort is basically, initially started as just a website, and you sign up, you make a sort of a login account, and you are presented with an image from this nearly 1 million large catalogue. And what you're asked is a series of questions. So you're shown an image and you're asked, in the first instance, is the galaxy simply smooth and rounded, or does it have no sign of a disk? And there are kind of template examples for you to look at and say, does this look like this, or does it look like this? So you don't actually need to know necessarily anything about the astrophysics or the astronomy side of things. It's just asking you to use your cognition, your vision skills, and your comprehension to classify various aspects of that image. And the flowchart here goes through the various different questions that are asked. So, how rounded is it? Is it circular or is it elliptical? And that tells us whether it's face on or whether it's edge on as viewed. And it asks questions, does it have a bulge at the center? Is that circular? Is that more angular, or is there no bulge at all? And if it's face on, do we see spiral arms and things like this, and how many of those spiral arms are there? And then there's a question very much towards the end where you can flag anything potentially that isn't included in this, maybe of interest for later follow-up as well. So the idea is that you ask a given person to look at a small number of these images, maybe in the low tens, and what this results in is a labeled data set of people's responses to this. And if you ask enough people, given a single image, you can build, extract trends from this, and also on average, if there's a bit of an outlier in terms of someone maybe got something a bit wrong, this will clearly show up in those classifications. So ask multiple people with the same image, and you get a really reliable, basically a labeled data set for all of these different galaxies. And this is really just a bit of an example of some of the images that are being shown or could be shown during the Galaxy Zoo process if you sign up. So you can see some of these are face-on spiral galaxies. Some of these are more elliptical galaxies with no structure. Some of them are quite large, some of them are small, some of them are edge-on. And this is basically just an example of the kind of stuff that you can be shown. And I think basically at the end of the Galaxy Zoo project, there were just over 100,000 volunteers that took part, and they made just over nearly a million different classifications of galaxies within those. So that basically allowed them to, the classifications were performed on multiple, the same image of multiple galaxies. So this really resulted in about just over 300,000 galaxies that were fully classified. And this has led to 77 peer-reviewed scientific papers. So this isn't just one publication, this is a huge swathe of papers that have been enabled by the results of Galaxy Zoo. And the average classification per user, if you take those numbers above, is about 8. So let's say a given person looked at about 10 images for this. So really the reward to effort ratio here is very high. This would probably take a person no more than 10 minutes. So you could do this during a coffee break at work, and this is what people do. It's really appreciated. We're very, very grateful that people are interested enough to spend their time doing this. And it really, really leverages the human brain's ability to recognize patterns, recognize structures that would be, in some ways, traditionally difficult to get a computer to make those same kind of comparisons. And the project time, really, from kind of inception into the results, so the first results, was approximately about 10 years. So I think roughly about 2007 this was started, and the first main results paper came out about 2016, 2017. So all in all, quite a lengthy process. So these citizen science approaches have been really useful so far, and actually I forgot to mention that on the previous slide, but this is now being applied to many different disciplines outside of astronomy as well. So anything from biology to ecology to chemistry. The platform that was used for Galaxy Zoo is now being applied in many different disciplines. It's called the Zooniverse project. So basically setting up similar kind of experiments for any kind of data in any research field that needs or would benefit from being looked at by a large number of people. So do take a look at that link and look for any projects you might be interested in across any area of science. It's a real help, and we do look for, we do really appreciate people's involvement. So going back to astronomy, then the citizen science approaches have been very useful so far. There's Galaxy Zoo, there's actually a huge number of spin-offs just within astronomy as well. So obviously that was to do with galaxies. There's also now projects looking at objects within our own galaxy. So planet-forming disks, for example, there's a disk detective Zooniverse project where you can do some very similar kind of things, and ultimately they result in labeled data sets that can be really useful for scientific research. But if we go back to this plot of the data volume as a function of time in astronomy, it's fair to say that I think astronomy will very soon, if not is already, going through a data revolution. So this is what happens in the future. So what we do is we kind of look at the expected data volume of upcoming facilities. These two are the LSST and the SKA. I will talk about later in the talk. But if we kind of run the numbers and work out what the expected data volumes are, then by about the end of this decade, we're going to be creating the same amount of data that is the equivalent of the global internet traffic in 2022. Obviously, the global internet traffic will increase as well, but we will be inundated with data that is, almost incomprehensible in terms of its size, its complexity, and one of the main questions is how do we deal with that as a field? There are probably less than, I don't know, maybe 10,000 astronomers in the world, professional astronomers. How are we going to deal with that volume of data? And actually, this really goes beyond even what's possible with these citizen science projects. So, we've gone from it's a 5 order of magnitude increase from what is possible previously. So really, we need something else to help. Yes, so that's exactly what I've said. And processing, analyzing, understanding that amount of data is far beyond anything that we can currently do that we've previously applied. But I think it's fair to say that we recognise this problem, and we also recognise that artificial intelligence as a broad theme is a potential way to address this, and probably the way to address this. And we can, what I'm showing here is a nice graph of an analysis of all of the research papers in astrophysics at the moment as a function of time. And what's been done here is that each of those publications has been searched for one of the 4 following phrases. So machine learning, artificial intelligence, deep learning, or neural network. And you can see that up until about 2015 or so, we were getting maybe in the low tens of submissions per month to journals, to scientific journals, mentioning these phrases. And then since 2015, this has exploded. It's really definitely the definition of an exponential growth here, where we go from the low tens of papers per month to nearly 100 papers per month mentioning these phrases. So it's clear that the astronomical community is recognizing the importance of artificial intelligence and how that might be applied to their research in the future. So it's really kind of taking off as an approach in astronomy. And I think to boil everything down, I think applications of AI in astronomy research can be split into three very broad categories. So in the first instance, this can be processing data. So as I mentioned, I hope I've demonstrated that we're really going to be expecting huge volumes of data that are going to be far beyond what a single human or even a large group of humans could look at. So as this data comes in from these various different facilities, we need to perform quality control on this and processing. This is not possible to do manually, as you might have done with a telescope that was operated by a single person in the past few decades. So we need AI to perform automated checking, quality control, a combination of data from different telescopes and facilities, make corrections for things like the atmosphere and the weather that's happening as the observations are being taken place, or any kind of error corrections that might be needed. Cosmic rays interfering with the detector, this kind of stuff. This is all really in the processing data side of things before we even look and try and do the science with those images, or indeed any other types of data that come from the telescopes. The second category is more kind of on the analysis side of things, and really looking at, once we have that science-ready data that's been checked and controlled for various different variables, we need to identify patterns. Really, the kind of astronomy is all about looking for patterns, correlations, anti-correlations in data. Do we see a correlation between this variable and this variable for those given objects that we're observing, and what does that mean astrophysically? What can we learn about the universe from those relationships, or even if there are no relationships in those, that's sometimes interesting as well. But what we have are often tens, hundreds, or even thousands of these variables, especially given the rise of the complexity of data that we have. So how do we look for these correlations or anti-correlations in an arbitrary number of n dimensions? That's something that a human brain can't do. We can look at a graph, as you know, the graph similar to the graphs that I've been showing you, and look at maybe two variables and see a correlation. We can look at maybe three variables, see relationships, but anything beyond about four is very difficult for the human brain to comprehend. We're three-dimensional beings, we are four-dimensional beings if you think about time. Anything beyond that is very, very difficult for us to get our head around. This is a real benefit of using artificial intelligence and machine learning to look at those correlations and report back on correlations between these many, many different variables in the observations. And then the third kind of area that I think AI will really help with is making predictions. So based on we've gone. This is kind of almost like a timeline of how astronomical research works. So we have the processing of the data, we have the identification of the patterns, and then given that knowledge, what do we think might happen in the future, or what might happen next? And examples of this could be predicting what we call transient events, so things that are not constant in time. A really good example of this is supernova. So an explosion of a massive star can happen without warning, but given enough information about the current state of what's happening with various different objects, could we predict the occurrence of supernova? Another good example that's very much on the different size scale is exoplanet research. So one of the ways that we detect exoplanets is that by the exoplanet popping in front of the host star and dimming that light. So if we observe one of those dimming events, can we predict when that might happen again? And what does that tell us about these exoplanetary systems outside of our own solar system? Thinking about on Earth as well, maybe not necessarily pure astrophysical research, but obviously the weather is a huge aspect of whether or not we can get a successful observation, certainly from the ground, obviously less important in space. But can we predict weather changes at astronomical sites with any certainty? Obviously, this is a weather forecasting problem, really, but it's certainly related to astronomy. And the more accurately we can predict good weather, the better we can plan our observations. And that can actually be applied to planets other than Earth as well. So we're now in a situation where we can look at the weather systems and patterns on planets in our own solar system. So, for example, Saturn, Jupiter, Venus all have thick atmospheres. We can look at the weather systems on there and try and predict what might be happening there. So that would be obviously very important for any probes or missions we send there. And also we're actually at the point now, amazingly, where we can look at weather patterns on planets outside of our own solar system. So these exoplanets that I mentioned, we're really, in the past couple of years, just being able to start to predict what might be happening in terms of their atmospheres and how they're redistributing the heat around their atmospheres, what they're made of. Are they rocky? Are they gassy? How do they fit into the architecture of our solar system? So all of these kind of predictions are areas where AI can really help us understand what might be happening in the future, and therefore plan the most appropriate and efficient observations to understand what's going on. So with those kind of three broad categories, what I'm going to do is just give you a very brief example of some applications of artificial intelligence in astronomy. This is definitely not exhaustive at all. I have just come up with things that I think are interesting. There are many, many other applications at the moment that I won't cover, and I apologize if I have missed out anyone's favorite application of AI in astronomy. So the first example, I think thinking about very close to home in terms of the universe, is the exploration of our own solar system. So really, this is as a discipline, this is probably more on the planetary science side of things than astronomy, but I think it's a really nice example of how AI can help. So if we want to go and, for example, send a probe or a mission to another planet or a moon in our solar system, then this is a difficult problem to optimize. This all depends on things like the vehicle design, what kind of rocket is it going on, what kind of propulsion does it have, what is the fuel capacity of that particular setup, when are we expecting to launch that, are there any delays to that launch, things can go wrong. These kind of probes take many decades to sort of build from the initial idea to the launch can be 20, 30 years. So obviously delays can then creep in from that. And that then really kind of depends on when you launch something, where are the targets that you're trying to aim for, where are the planets in the solar system at that given date, and how can those planets or the location of those planets affect where you're trying to send things. So a really nice example of this are the Voyager 1 and Voyager 2 probes that were launched in 1977. So I'm sure you've heard of this before, but this was colloquially referred to as the Grand Tour of the solar system. And the reason that this was able to be a grand tour was quite a unique configuration of the planets in the solar system. So you can see in this graphic here, the launch dates, 5th of September and the 20th of August in 1997 from Earth. And because of where the planets were located, these probes were able to intercept Jupiter, Saturn, Uranus, and Neptune in our solar system, so the outer giant planets, really quite easily. Had the planets been in a different configuration, this wouldn't have been possible. So you can imagine that if you put Neptune on the other side of its orbit, for example, that we couldn't have sent a probe to go and to look at it. It wouldn't have been physically possible to get the probe to go on that trajectory. And actually, this was almost discovered by accident. This chance configuration of Jupiter, Saturn, Uranus, and Neptune was discovered by someone at NASA who was looking into this, quite a junior researcher, as I understand it, who then took this to their superiors and said, "Listen, this is a very rare event that we can take advantage of. Let's try and take advantage of it." And I think the similar kind of configuration isn't going to happen for another couple of 100 years. So it really was a unique event, and it's wonderful that we were able to take advantage of it. But this kind of optimization problem is very difficult to look at in terms of predicting when the next favorable situation might be, and this is where something like a deep neural network can come in and predict things in the future, but also if it's trained appropriately, could sit on board one of these spacecraft and conduct real-time guidance and navigation. So it could be possible to make real-time changes to various different trajectories and things like this based on the influence of external factors. And another thing I'll mention in the next example is, we can't reliably make changes to these missions from Earth just because of the time it takes for a signal from Earth to get to these locations. The speed of light is not fast enough for us to really steer and command these probes with any great accuracy. So I think that, for example, one of our nearest planets, Mars, it would take 8 minutes for a signal to get from Earth to Mars. So if you're imagining, a last-minute course correction or something like this, it's 8 minutes for the signal from Mars to get to Earth, and then it's 8 minutes for a response signal to get from Earth back to Mars. So you're talking about nearly 20-minute delay for any kind of real-time changes. So imagine if you're driving a car with a 20-minute delay, this is not really safe. This is not really useful. So the same problem optimize for this kind of stuff. And actually, it just gets worse as you go further and further away from Earth. So even with the closest planet, this is an issue. So I've mentioned Mars. So the next example is appropriate here. So once we think about actually getting to a location, the landing site and mission route paths are something that can be difficult to determine a priori, so before we go. And normally what happens here is that the terrain maps are manually inspected. For example, for Mars, we have very good maps of the surface from orbit, from different missions. But if we have landers on the ground, they may encounter things that we haven't seen. And this has been seen many times before with some of the rovers on Mars, where we pick a landing site, and actually once the probe has landed, it finds out that it's much steeper than the terrain is much steeper or much more irregular than we might have thought of initially, and this presents real problems for if we then want to send that probe and go and explore around the region. So there's a really nice example here for the Mars Perseverance lander that was published in the paper that I'll give the reference for on the bottom there, where there was an automated classification of the terrain and an analysis of the particular routes that this Perseverance lander could go through, which was then able to react in real time after landing. So basically there was an optimal route planned, but as the lander and the probe, Perseverance rover, gathered more data as it landed, after it landed, as it scanned the terrain, it was able to pick out the most optimal route to go for in terms of looking at areas of interest to investigate, and also to avoid hazards and things like this. And this is all possible due to training networks and artificial intelligence. So it's a really nice example of how that might be applied for missions in our own solar system. And then thinking a bit more about general astronomy, really most of the time what we're doing is effectively taking photographs, right? We're using big cameras on observatories around the world to photograph and analyze the night sky. But there are many more astronomers than there are telescopes in the world, especially the big complex telescopes that are really making those exciting discoveries. And they are oversubscribed for time. So what we do is we apply for time on these telescopes, and the most in-demand telescopes have oversubscription rates of 15-1. And that means that for every 15 astronomers that apply to use that telescope, only one will get time to do their science. So one of the questions that we can ask is, can we learn to do more with less observing time? So if any of you are photographers, you know that integration time, or the shutter opening, the longer you leave your shutter open, the more detail you get in an image. And what we want ideally is long exposures on the sky to pick out the highest detail. So on the images that I'm showing here, you can see an example from the Hubble telescope again, what a short exposure might look like in terms of the top left, and what a long exposure would look like in terms of the top right. So you can see there's much more detail that is apparent in the long exposure, and that makes understanding the science and doing your analysis much easier. But obviously, if everybody asks for a lot of time on these telescopes, then the time available goes down. So there's a trade-off between doing the best science and allowing more people to do their science as well. So can we learn to do more with shorter exposures and less observing time? So this is a nice example of where this particular paper here that's given at the bottom has used a convolutional neural network to almost fill in the blanks for short exposure images. So this was trained on what long exposure images look like, and then it was applied to look at and correct and enhance the short exposure images. So you can see at the bottom here there are two examples, the CNN1 and CNN2, where what they've done is basically take that short exposure image, run it through the neural network, and predict what a long exposure would look like. And this is, as I said, this is kind of enhancement, but also removing noise from the image. So you can see that the noise level has really reduced. The signal to noise ratio is much improved. And actually, those neural network processed images start to look like the long exposure image, the true real life long exposure image. So it's a really nice example of how we can improve the efficiency and get more people doing the science that they want to be doing by using things like artificial intelligence and neural networks. Okay, so they were kind of three, as I said, not exhaustive examples of how AI in astronomy is potentially being applied at the moment and helping us understand things. But what I want to talk about next is a bit about the future of AI in astronomy and where those applications are going to be used in the coming years. So what I'm going to do is show you a series of short videos on various different missions that are either operating at the moment or are coming very soon. And the first of which is the Gaia Space Telescope. So I'm just going to hopefully play this now. I apologize if that's a bit loud. Sorry, I'm being told that you can't actually hear that video. Sorry about that. Bear with me 1 second. Let me. I'm not sure how to correct that, but let me try and talk through it as we're going. So basically, the Gaia Space Telescope is a mission that has been put into space, and it is mapping the entire sky. So it will produce a huge catalogue of the positions and locations of stars in our Milky Way. And as time goes on, it will track the changes in positions of those stars and basically build up a three-dimensional map of how all of those stars are moving around our local area. And it will also it will look at the positions, it will look at the velocities of those stars and how they're moving, how they're maybe moving away from us, how they're coming towards us. And that gives us almost a movie of the local environment that we can play forward, play backwards, and look at how, where those stars may have formed and also where they're going in the future. And this is a nice example here of how those stars are moving around our local area of the Milky Way. And I'll just jump forward for this next part here. And once Gaia is complete, it will have a final catalogue of 1 billion stars in our local neighbourhood. So this will represent actually only about 1% of our Milky Way galaxy. But this is a huge database of the positions, locations, and velocities, and also things like the composition of those stars. So there's many different parameters, those variables that I was talking about earlier. this will represent a really huge data set to look at. And the way that Gaia is operating is basically every couple of years there is a data release. So I think we're currently on data release 4, and data release 5 will be the final data set that's coming in the next 3 or 4 years or so. So there's already Gaia data to play with, and actually at the end of the talk I'll give you a link to go and look at some Gaia data yourself. But machine learning techniques are obviously needed to really kind of delve into this unique and really valuable archive and database. And a really nice example of that, I think, is by actually an ex-University of Leeds PhD student, Miguel Vioc, who's now working at the European Southern Observatory in Germany. And he used an AI system to analyze this catalog. I think it was actually data release 3 from Gaia. And he was able to find 2,000 new young stars in this database that we didn't know about previously. So these were in what were called Herbig A/B stars, and they're a really kind of unique class of young stellar object. And this graph here shows the number of sources that were previously known, and the blue shows the kind of the new sources that Miguel was able to identify using AI. And this is something that wouldn't have been possible using with manual searching or anything like this. It was the data volume is entirely far too big for this. So it's a really nice example of how you can use machine learning to search for new astronomical discoveries, and then obviously what we can do with these stars now is then follow them up with other telescopes and other facilities, which is ongoing at the moment. So this was a paper that Miguel wrote in 2022, and there are follow-up observations planned for looking at these newly identified interesting objects. Okay, so I think there's a bit of a problem with the audio, so I will attempt to talk you through this. So this is another example of in fact, well, there's subtitles here, so you can hopefully follow along, but I'll talk you through it as well. This is an example of another facility that's on the ground that's being built at the moment, called the Vera C. Rubin Observatory, and this, in a similar way to Gaia, is a survey telescope. So this will survey the entire night sky every 3 or 4 days for a total of 10 years, and it has a huge camera and huge lens on the telescope that I think actually are the world record for the largest CCD, the kind of the camera chip, and also the lens that's on the camera itself. And as you can see there from the image, there's going to be 1,000 full sky images over the next 10 years or so, and this will produce nearly 200,000 images of the night sky per year. And the reason that this is a really exciting mission is that we're going to be able to look at changes in the sky on very short timescales. So we're basically going to be looking at how the night sky changes every 3 or 4 days, and this is invaluable for looking at things like those transient events that I was talking about here. So everything that may change from one night to the next, we'll be able to look at how those changes have occurred, how those things are moving across the sky. So a really nice example of that is the asteroids in the solar system, or variable stars, things that are maybe going supernova, things like this. And you can see some examples in the video here as well. So this is a really nice opportunity, an amazing opportunity, but it presents a real problem in terms of data storage and processing. So I think the examples at the moment, the storage and processing respectively will require 100 petabytes of data and 250 teraflops to process that data. And once we do that, then that will be incredible, and there'll be an annual release of data that will eventually include a catalogue of 37 billion sky objects. Each of those objects will have over 200 attributes. So there's 200 different pieces of information for those objects. So this is really a big data problem, both in terms of the processing and the analysis of that data. And really, we're going to have to be looking at applying AI techniques to the processing and the understanding of that data as well. Finally, I'm going to talk a bit about the facility that you may have heard of called the Square Kilometre Array. And again, I'll just let this movie play, but I'll talk through what's going on. So the Square Kilometre Array is a next generation radio interferometer. So rather than thinking of a traditional telescope with a mirror and a lens, this is more a bit like a satellite dish. And actually, it's a series of satellite dishes that are connected together. You can see in the image here. In fact, it's two telescopes. So there's SK Mid, which is going to be located in South Africa in the Karoo Desert, and SK Low, which is going to be located in the Murchison area of Western Australia. And you can see here, this is a bit of a video of SK Mid, the ones that look a bit more like the satellite dishes that you may have seen previously. And what I'll do is actually just jump to some images here. And SK Mid really will be transformative because there'll be 197 different antennae located across South Africa, and they're connected together in a process of what we call interferometry. So we simulate the capabilities of a larger telescope by connecting together smaller telescopes in a clever way. I won't go into the full engineering and science behind it, but we can basically build up a much more capable instrument by connecting those telescopes together. And really, the scale of SKA is enormous. It is being built at the moment. So the first dish was delivered to the Karoo Desert a couple of months ago, and you can see the comparison of scale here. So this is an example of an artist's impression of the dishes, but you can see the truck that is stationed there. And actually, this is the prototype that has just been installed in the Karoo Desert at the moment. And you can see here the size of those cars and the people actually standing underneath this dish. So this is absolutely enormous. It's about a 10-story, the size of a 10-story building, and there's going to be 197 of these dishes. And this is going to allow us to look at radio waves from the universe. And this has a huge range of different applications across astronomy. So everything from cosmology to pulsars, to cosmic magnetism, to observations of objects in our own galaxy, and also thinking about where we came from, our origins in terms of the universe, and things like how we form planets around other stars, and whether they might support life or do support life currently at the moment. So there's one aspect that SK is going to be able to look at is the search for extraterrestrial intelligence. So it's really a transformative instrument across many different aspects of astronomy. And it's being described as the largest IT project in the world. And the reason for this is really that it's an information and communication technology super project. So that the data rate from that telescope to the processing center that's going to be in Cape Town in South Africa is going to be 20 terabytes per second. So that's how much data it's going to be collecting. And processing all of that data is going to require 135 petaflops, which actually, if you do the calculations, the computer required to do that would be one of the top 3 fastest supercomputers in the world as of 2020. So the machines needed to look at this are really enormous. They're really large scale projects, and this is now being brought together so that SKA can begin operations hopefully towards the end of the decade, around about 2028, I think is the latest estimation. And really, we're going to need artificial intelligence at every stage of SKA So we're going to have to process that raw output. We're going to have to perform the quality control. As I mentioned before, we have to convert it to formats that are science ready, so we can do our science on it. We have to characterize those huge data volumes. We have to analyze those results, and also we have to plan for future observations. So really, all the way through that process, it's beyond what we can do as humans. So we will need AI to apply various processes at every stage of operation of SKA. And this is really potentially the first phase of SKA. And I think something to really hammer home is that SKA is planned to be a much bigger endeavor as well. So it's currently located, or the first phase will be located in South Africa, but the plan, the hope, the aspiration is to extend that to many different African countries. You can see here, this is the potential layout of SKA Phase 2, where we extend those dishes and we place dishes in many different African nations and build a huge virtual telescope that will have 10 times the sensitivity of the first phase of SKA and 20 times the spatial resolution. And with that increase, it's potentially orders of magnitude more information and more complexity to understand. So we certainly will be needing AI, data science, machine learning to help process data from this kind of phase 2, which is certainly not around the corner. This is the next 10, 20 years plan. But one thing to kind of mention with that is that it presents a really nice opportunity for global collaboration in astronomy and astrophysics across Africa. So what we want to ensure is that this isn't just placed across Africa, and we want this to be a global collaborative effort. And something that has been trying to help with that is what's called the DARA project. So this is the development of Africa with radio astronomy, and this began in about 2015. To help develop a range of high-tech skills across the African partner countries for the SKA. So we want to basically make sure that African researchers are able to help build, plan for, and use SKA in the same way that anyone else in the world can as well. And DARA has been a really nice project in that it's developed a cohort of expertise in radio astronomy and related disciplines, and delivered about basic training in astronomy to about 320 young people. DARA has produced 43 master's students in various aspects of radio astronomy, and 13 PhD students. And of those numbers, 17 of the master students and 4 of the PhD students were concentrating on big data aspects of radio astronomy across Africa. So that's really nice to see, and obviously very appropriate for what we're talking about today. And here are just some examples of various different events that DARA took place. So in the top right there, you have the annual network meeting from one of the previous meetups. I think this was in Stellenbosch in South Africa. And you can see in the top left some of the students actually working with their own radio telescope, working with a DARA graduate there, so building their own radio telescope and understanding how that works and how they can analyze data from it. And the bottom there is the leader, the initial principal investigator of DARA, Professor Melvin Hoare, with the first cohort of PhD graduates from a program there. And that's actually on the roof of our department at the University of Leeds. So you can see it's very, very British. There's not really any sun in the sky there, unfortunately. But DARA is a great opportunity to develop skills, and actually Phase 3 is in operation at the moment. It's just been funded and just starting up, and the plan here is to train a further 450 people in radio astronomy skills and establish radio astronomy research groups across Africa. So we're really excited to see how that develops, and it's a wonderful opportunity for collaboration across the world. So I'm just going to kind of finish up here with giving you some just examples of where you can find various different resources for AI in astronomy. So the AstroML project is a really nice example of a combined kind of Python module, Python examples, and actually a textbook for various aspects of machine learning and astronomy. So I'd really recommend you look at that if you're interested. Going back to the DARA project, the many lectures and seminars for the training, particularly the basic training side of things, is online. There's during COVID, obviously, a lot of these in-person events were impossible, so a lot of this went online, and it's still online. So if you're interested in looking at all of that, you can find that on the YouTube channel for DARA there. I'd point you to particularly to a wonderful talk by Professor Anna Scaife from the University of Manchester, where she talks about AI and bias in astronomy. So that's a really important aspect that I haven't covered today, but hopefully you can look at and see what some of the problems might be with applications of AI in astronomy as well. As I mentioned previously, one of the nice things about astronomy is that we make data almost publicly available most of the time, so you can look at Gaia data yourself. And there's a nice application here called Gaia Sky at that link where you can go and investigate and play with the Gaia data yourself. So it's really nice. A nice thing to have a look at and see how you can understand the local universe. Just a nice example of some astronomical data that's already set up really nicely for some machine learning frameworks like JAX and PyTorch and things like this. There's a GitHub repository there called Astrods by Maggie Liu from the University of Nottingham. And if you're interested in future things that are happening in terms of AI and astronomy, there's a meeting at the European Southern Observatory in Germany in September, this coming September, that will be live streamed and broadcast on YouTube, looking at how things like large language models might be able to help understand astronomy and drive things forward in the future, which is something that I've certainly not touched on today, but is an entire other aspect. So just a quick summary. I think it's, I hope I've convinced you that astronomy is undergoing a bit of a big data revolution, and the combination of astronomy and AI is essential at the moment, and is going to be even more important in the future. There's already many examples of this, and there's many more use cases to come. And really, these all come at every stage of astronomical research, whether it's planning the observations, whether it's processing the data, whether it's performing the analysis, or making predictions for the future. And I really hope I've convinced you that it's an exciting field to apply your AI expertise in, although we might still have some way to go. So this was a prompt that I put in just this morning to create an image for artificial intelligence and astronomy, which isn't maybe the most representative of the real world, but there's still some way to go. So with that, I'll say thank you very much, and I'm very happy to take any questions.
Yes, thanks, John, for the wonderful presentation. So shall request anyone who has a question to type in the chat Q&A, or if you can speak, just raise your hand, and then we shall enable the mic for you to speak. Yes, blessing or something, you can speak now.
Oh, sorry, could you, if you asked a question there, I was muted, so could you please repeat?
I just want to appreciate you, done a good work, you explained. I've just joined this is my first time, and I would like to the session, and I hope to be joining every program. Thank you. That's all I can say.
Thank you very much. No, that's really, really kind.
Any more questions? Can just raise your hand and we shall enable the mic for you. Or you can type in the Q&A.
Oh yeah, okay. So we have a question from Angel. So I'll just repeat that for everyone. So my question is about getting involved. Astrophysics is a field that we haven't tapped into much in our country. How can we get involved? So it's a really, really good question. And I think that really comes down to the DARA project that I mentioned. So we've been very fortunate to receive further funding for DARA. This was quite recent, so things are happening in the background. And as those opportunities and those various different opportunities develop and solidify, I'll be very happy to share all of those with deep learning with Bruno, who can hopefully pass those on as things become available. So I guess my answer is a bit unsatisfactory in that I'll say watch this space, but hopefully there will be opportunities to get involved and apply machine learning skills and stuff in the future. Yeah, so I have another question.
I see a hand up. Daily Blues. Yeah.
Um, all right. Thank you for the opportunity. Probably my question will be how much detail can this AI provide about the astronomy of?
Sorry, I think you broke up a bit there, but I think the question was how much detail can AI provide about astronomy? So I hope that was the question. I'll try and answer that. I think that's a very good question. It would really depend on the application, and I think something that I didn't talk about that is covered very nicely in Professor Anna Scaife's talk is what can happen, or what are the downsides of AI application in astronomy. So I'm sure if you haven't already covered this, or you may already know that really the things like neural networks are only as good as the training data that they work on. And if there are any problems with that training data or any biases in that training data, then this can then be propagated onto whatever that network or process is applied to. So we have to be very careful in kind of the application of this. And there's the big effort to really understand what might happen in terms of any application of these kind of tools and what might be spurious that's introduced into those processes. So what I guess in summary, what I'd say is that we have to be very careful to not treat these kind of tools as black boxes where we don't understand how they work, and we should really try to really well characterize what they're doing so that we understand how they're kind of applying their processes to the data in whatever format that may be, and making sure that we're not introducing incorrect results or any errors into that data process, and that's something we have to be careful of.
Okay, thank you.
Thank you.
Any more questions? You can type in the chat or you can raise your hand. Well, maybe just to reiterate that we shall have a workshop during IndabaX Uganda 2024 on astrophysics. That's as astronomy, as John put it. Somewhat different words, the meaning. Yeah. Yeah, so we hope to have you guys join the workshop. Yeah, it will be physical, and we shall have facilitators flying in, come and take charge of that workshop. So more details will be shared when the application process opens up. Yeah. So any more questions? John, you wanted to say something?
Yes, I was just going to say if anybody either comes up with some questions in the future, or if anybody is watching this offline, then if you have any questions, please feel free to contact me at the email address provided on the slides. I'm very happy to answer anything as questions come up.
Okay. Is there another question? Oh, just thank you. Okay. Is there a hand up? Does someone put a hand up? Okay. Yes, you can speak.
Maybe my question is like, maybe Jamie can provide us with the email or any platform where you can reach out to him in case you want to ask or want to know more. Thank you.
Sorry, the connection is a bit bad there. I didn't quite catch that. Maybe if you could type in the chat, if that's possible.
Yeah, I think he was talking of sharing the email address. I think those are details we shall share when we in the mail when we share the recording with everyone who had registered to attend the session, and yeah, so we shall share the link to the recording and also the PowerPoint presentation, which will have those details that like email and everything. Yeah.
Yes, and I'm aware I put a fair few URLs in there that I'll share with Bruno so that you can put those in the email as well. There's a question in the chat about asking if there's any social platform channel where we can get these resources. I don't think there's any single place, but hopefully the links that we put and share around will point you to some useful resources. Yes, and we'll share the email address with you all as well. Yeah, sorry, I didn't leave that up for very long on the slides.
All right. I think as we bring the session to an end, we shall be sharing the resources in May. That is before the end of this weekend. Yeah, because we had quite a number of people who had signed up to attend the session, but I think the timing, yeah, so, but everything will be shared, the PowerPoint presentation and the recording itself. We shall also upload the recording on our YouTube channel. Yeah, to make it available to the public, and yeah, we shall keep you informed on any other developments that might arise. Maybe John, if you have a few last words to say before we sign off.
Well, just thank you again for the opportunity for coming to speak to you. It's been a really enjoyable morning, and I hope you all have a wonderful Easter weekend.
All right. Thank you, John. And you won't be coming to Uganda, unfortunately, but would have loved to to have you.
I know I'm very sad, but I will be sending some very very appropriate replacements.
All right then. All right. Thanks. Thanks, John, and have a wonderful Easter weekend.
You too. Thank you very much, everyone. See you soon.
All right. Okay, bye.